So we just talked about statistical learning with one discrete numeric predictor. What does it look like to do statistical learning with a continuous numeric predictor? Suppose we want to know the mean 2023 salary among Major League Baseball players who in 2021 earned $5 to $10 million. We might care about this question if we wonder if there's aspects of cumulative advantage, where those with high salaries tend to have salaries that continue going up in the years to come. Here are some data that can help us answer this question. So this is our same Major League Baseball data that I scraped from USA Today, where we have the salary in 2021 on the x-axis and the salary in 2023 on the y-axis. Each point corresponds to a player. Here we'd like to know the average salary in 2023, the average y value, among the players whose 2021 salary was between $5 and $10 million. So we want to know the average y value of all the points in this white space of the plot. Now suppose instead of the whole population, what we have is a sample. So we take a random sample from all the players, and the blue dots correspond to the people included in our sample. Then how could we use this sample to learn the average salary of all the players in the white strip? I'm going to assume that we know the 2021 salary of all MLB players, but we only know the outcome, the 2023 salary, for the sampled players. So one approach is to just restrict to the sample who fall within that target population. We could take the average salary of those players, and that would be an estimator, the sample average in the subgroup. Now we could do this again and again. We draw a new sample, focus on those in the target subgroup, and record an estimate. New sample, focus on the target subgroup, record an estimate. And we could keep going this way until we get a whole distribution of that estimator across hypothetical repeated samples. Similar to our example in the last video, this is going to be a high variance estimator that's unbiased for the target population mean. So how would you use a model to answer this question? You might pause for a second and think about that. Okay, how would I use a model to answer this question? I might begin with my population and draw a sample. Then in my sample, I would fit perhaps a best fit regression line. Now this regression line can't just lead to a prediction that directly answers our question because it's not clear where along the x-axis to make that prediction. You could predict over here or in the middle, and you might get a different predicted value for y. So we can take that model and we can then predict for all the people in our target population. This is all those players, sampled and not sampled, who fall within this particular range of 2021 salaries. For all those players, we can make a prediction, their predicted salary in 2023 based on the regression line. Then we could average that prediction to produce an estimator. I'll walk through this again in a new hypothetical sample. So we have the population, we draw a sample, fit our best fit line, focus on our target population, and make a prediction for all those people in the target population, whether or not we directly observed their outcome. And we average that prediction to be our estimator. This is a way we can use a model to make an estimate for the average outcome across a set of people who have different values along this continuous numeric predictor. So continuing in this process, we can imagine sampling, learning, and recording our estimate many times. And as we do that, we'll see that we have a distribution of estimates that result. And here, because our linear regression model, it might be wrong in some sense. It might be the case that the pattern is not really linear. Perhaps there's actually a little bump up that corresponds right to the region where we're interested in the outcomes. This would cause our linear regression estimator to be downwardly biased. It tends to be a little too low for the estimate within this region. So the ordinary least squares strategy, to recap, is to take our sample from the population, learn a model in that sample, and then predict for all the people in the population who we're interested in summarizing. We then just take the average over all those people. So this leads to a question, how would you do this with a machine learning model? This curve here is actually a low-S curve, which is a locally weighted regression estimator, but you don't really need to know that. For now, let's just think this is a black box model that takes a sample and results in some curve. This curve gives predicted values. When you give it an x value, it gives you a predicted value for y. So how would you follow this procedure with machine learning? It actually looks exactly like the procedure for ordinary least squares. We begin with our population, draw a sample, and then learn a model from the cases in that sample. We then focus on our target population and predict the outcome for all the units in that target population and record the average. We can repeat this process many times, getting a whole range of estimates based on sampling uncertainty. And as we do that, we again get a full distribution of possible estimates. So here we've come to a place where we have three estimators. We have the sample mean, the linear regression estimator, and this new machine learning estimator. In the next video, we'll talk about how we can think about some properties of these estimators and how we might choose one over the other.